In this situation, we have a narrow passage, something like this, and the fish are passing through, right? And based on our observations, right, we know the average rate. Every hour, there are 5, got to work with my very limited artistic ability here. There are 5 fish that pass through this thing. Now, keep in mind that saying the average rate is constant isn't the same as saying the rate itself is constant. In a given hour, there may be more than 5 or less than 5, but on average, we know this is how many we can expect. Since we know this average rate, we should be able to talk about the likelihood or the probability that a given number of fish pass through at a given time. Right? And the model that describes this kind of scenario is called a Poisson distribution. Right? It's named after the French mathematician Simeon Denis Poisson. So, just like we saw with the binomial distribution, right, there are some requirements that have to be met. The first one here is a little technical, but what it's saying is that it isn't possible for 2 events to happen at the same time. That's why in my salmon example, the channel had to be narrow, so that only 1 fish could pass through at once. Right. Second, the probability of success can't change over time. This is similar to the binomial distributions rule that the probability had to be the same for every trial. And finally, the number of successes over one time frame doesn't affect the number of successes in other time frames of the same length. And this is kind of the Poisson way of saying that there has to be a level of independence in the results that we see. So I've got some examples here for us to look at and see how we can apply these 3 requirements. Now, we already talked about my salmon scenario. Right? The narrowing of the passage means that only 1 fish can pass at a time. It's also reasonable to assume that the rate is going to be constant at all times of the day, and that the behavior of 1 fish doesn't impact the behavior of other fish. Right? So all 3 requirements are met. Okay, so scenario 2, this will also qualify as a Poisson distribution. Assuming that it's a single lane drive-through, right, only 1 car can pass through at once. And since we're restricting ourselves to a specific time frame, it's reasonable to assume that the rate of cars passing through will be constant and that 1 car's behavior won't affect the behavior of other cars. Now, with all of these situations, you have to be willing to qualify this a little bit. For example, if there's an accident at the opening to the drive-through, okay, now that 1 car's behavior did make a change. That's something we don't expect to happen, right? We usually aren't considering unusual circumstances when we're answering these questions, but as a researcher, you do kind of have to have that in the back of your mind, since if there was a day when this happened, any data you tried to collect from that day would probably not be valid, or at the very least you'd have to do some serious qualifying to make sure everyone was aware that this special case had happened. All right, now scenario 3 isn't going to qualify. An intersection could have lanes, right, going in both directions. Like this situation, you've got cars going north and cars going south, right? Which makes it possible for 2 cars to pass through the intersection at the same time. So requirement number 1 isn't going to pass in this situation. Right, now scenario 4 fixes that by narrowing the view down to a single lane, right, going in a single direction. All right, but we can still potentially have issues with the second criterion. Traffic patterns change over the course of the day. So the probability of a given number of successes during rush hour wouldn't be the same as in the middle of the night. Now, this could be fixed, right, by adding a restriction similar to the breakfast rush time frame that we had up here in the second scenario. All right, so now that we've seen how to identify a Poisson distribution, the next step is to come up with a formula that we can use to actually calculate Poisson probabilities.